Chapter 16, Lesson 2. In this lesson, we'll talk about pH, which is an extremely important concept when dealing with acids and bases. So, pH has a strange definition, but pH is defined as the negative base 10 logarithm of your hydronium ion concentration. Recall, hydronium ion is what really comes from acids. So what we're checking in a strange way is the concentration of the acid product in the water. And the log, if you remember from mathematics, what the log does is it undoes the times 10 power, because in math the numbers system that we use are based on 10, and actually that's what we've been using scientific notation, numbers like 1.8 times 10 to the negative 4th or something. What this does is it undoes the power of this 10, or of this exponent, you could say. So anytime you're checking for the pH of a solution, you're checking for the power of that concentration. So if you want to take and find out the concentration if you have a concentration, in other words, of acid in water, and if it's this concentration, then the pH will technically tell you what would the power be of that concentration in an indirect way, and hopefully this will make more sense as we roll along here. But sometimes it's convenient to think of this as the power of hydrogen, of H+. Very often it is referred to as the power of H+ in solution, really how much H+ you have in solution. So in pure water, and now looking through the eyes of equilibrium, in pure water we set this equilibrium constant up last time. Your hydroxide and hydronium ion concentrations are the same in pure water. So the way we solved for this is if you take the equilibrium constant and solve for just the concentration of any one of these, you'll get both of them to be 10 to the negative 7th. And we mentioned this last lesson, but this is the concentration of both H+ and OH- in solution, both of these, in pure water, you can say. And so we can then define the pH of a pure water solution. And if we do that, if we take the negative log of your pure H+ water solution, you'll find that the pH is 7. Now you may recall from earlier classes, you probably knew that the pH of water is 7, but here we show you why it's 7. It is because the concentration of H+ in pure water is 1.0 times 10 to the negative 7th. And notice as we negative logged it, that negative 7 was the power, and that's how we got 7 for the concentration of or for the pH of pure water. So in general then, if you have a solution that's acidic, then an acid provides more H3O+, and therefore the pH will be less than 7. And it's going to be less than 7 because if you analyze the power, if you have times 10 to the negative 7 versus times 10 to the negative 5th, which number is bigger? Well, obviously this number is bigger. Therefore, the smaller the power, numerically, the higher the concentration. And that's why the more acid you have, the lower the pH. And a base has an H+ concentration then that is higher than 7. So 7 is kind of the division mark. The higher than 7 will give you a base, lower than 7 will give you an acid. And here's kind of an overview of the whole issue. So a neutral solution will have a pH of 7, an acidic one will have a pH that's less than 7, and a basic one will have a pH that's higher than 7. And correspondingly, the H+ and OH- values. The higher the H+ value, the lower the OH- value is the idea. Here are some common substances and their pH values. So your absolutely pure water is right in the middle. Notice how pH is based on water. So this whole idea of acids and bases are based on water. As you go into the acidic this side here, your HCl, 1 molar HCl, has a pH of 0. In fact, if you do negative log of 1, what you'll get is you'll get 0. And that's how we define that. And then gastric juice is actually the acid in your stomach that helps in digestion. And then you have a lot of weak acids here that come from fruits. Milk is extremely weak as an acid. And then as you go toward the basic side, you have the strongest base is your sodium hydroxide. This is your strong base. And a 1 molar solution of sodium hydroxide will have a pH value of 14. Technically, our pH scale goes from 0 up to 14, even though it could extend slightly more into each side. Your bleach is your famous strong base, quite strong, and there are many cleaners and detergents at home. Most of your cleaners are actually basic. So this is kind of an overview of some basic substances, or common substances that are either basic or acidic. So we can now calculate the pH values for these. So first is a solution which has a hydrogen ion concentration of 0.010. Recall that pH is simply the negative log of the hydrogen or hydronium ion concentration. So if we negative log this value, 0.010, we'll get the pH. It's as simple as that. So if you plug this into your calculator, find your log button and try this, as we will be doing a lot of these sort of calculations. So take the negative log of 0.010. In some calculators you may have to put 0.010 first, then click the log button, and then click the negative sign. But you should get yourself an answer of 2. Now what this means is the concentration. If you think about this concentration here, 0.01, as being 1.0 times 10 to the negative second. Well, this negative second is the power, and that's what pH does. pH pulls out this power. And that's how we get 2. So if it's very often you can actually see the pH without having to do the calculation. If the concentration is a little less clean, like it is in this case, let's calculate the pH here. By the way, pH has no units. pH is unitless, because it's really the power that is in that concentration. pH is usually unitless. Now here we have an OH minus concentration. This is going to be a basic solution. So here we have to do a little more work. So first, why don't we try to find the H plus concentration? And to do so, we'll use our kW definition that we've seen just previously. Remember kW, which is 1.0 times 10 to the negative 14, was equal to H plus times OH minus. And so we can get first the H plus concentration from this equation, and then we'll plug that into the log. So your H plus concentration, with the equation rearranged, is 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5th. So try, little negative got away. So try that in your calculator and see what you get. And hopefully you got yourself, this is, we actually just solved this I think previously. We got 5.6 times 10 to the negative 10th. We've tried a similar example for your H plus concentration. And now we can plug this into negative log. Your pH then is negative log of this value, 5.6 times 10 to the negative 10th, and plug this into the value, and you should get yourself a pH of 9.26 as the value. Again, This is unitless, so just 9.26. Now notice this is basic because we are above 7. So we are definitely basic, and which is consistent because we have a hydroxide ion concentration that we're talking about here. So this is how we use the concentrations to determine the pH. And pH, really, by looking at the pH, you can roughly see the concentration that's in the solution. And that's what we're going to go. What if we go backwards? Now, we can actually, like any other equation, can be rearranged to give us the opposite solution. So here is our pH equation. So we're going to rearrange it to solve for H3O+. And first, let's move the negative to the left side by multiplying both sides by negative. And then to undo log in algebra, you raise both sides to the 10th. So if you, in order to undo logs, because this is log base 10, here's how you would do it. And this essentially cancels out. If you don't know how to, if you haven't seen this, then just kind of go along with it. Just remember this equation. This is then the final equation. If you want to get your concentration of hydronium ion from pH, you simply raise pH, you raise 10 to the negative pH, and that is how you will do it. So we're probably going to do a quick little calculation. So we have some freshly squeezed apple juice for your enjoyment as you are listening and discovering the concept of pH, and that has a pH of 3.76. So we would like to know, well, how much H plus is there in this apple juice? And let's plug this into our equation. Our equation says that H plus is simply 10 raised to the negative pH. Well, our pH is 3.76, so 10 to the negative 3.76. Try this in your calculator. Should give you the hydrogen ion concentration. And hopefully you got something like this. 3 zeros, 174. And they'll still be molar because we're asking for the molarity. Remember, these brackets mean molarity. So pretty easy. Essentially we're undoing the pH. Now this P that is in pH, since P means negative log, this can actually be applied to many other measurements in chemistry. So we're going to see this actually later on, but you can apply it to the OH. If you have the hydroxide ion concentration, you could talk about something called the pOH of the system. So you negative log the OH minus concentration. You can even do this to your equilibrium constants, and this is also very famously done. You can negative log your acid equilibrium constant. We'll actually take a look at these next time in the next lesson. So the story here is that this negative log, this P, can be applied to many measurements. Now here's a quick little trick to help us solve for the pH of solutions. We defined the dissociation of water and its constant, Kw, to be the product of H3O plus and OH minus, which gave us numerical value of this. If we apply the properties of logarithms, which means if we just negative log everything here, we apply negative log to absolutely everything in this equation, mathematically what that gives us is this equation. Now I won't go into the explanation of how this works, but the properties of logs say that if you add logarithms, you can get yourself to this point. We said that the negative log of Kw, just negative log of this number, gives you 14. That's how we undo the power. And then you end up with this powerful equation. And you may have seen this in previous chemistry classes as well. The pH of a system plus the pOH of a system gives you 14. And here is now, this is kind of summarizing all the equations that we've just went through. This is something called a pH map. It may help you do some calculations. So if you want to go from H plus to pH, this is how we simply negative log. pH is the negative log. If you want to go the other way, you do 10 to the negative pH. These are oriented a bit strangely. You can do the exact same thing now with OH minus. To get to pOH, you just negative log it. Here it is. If you want to undo that, you do 10 to the negative pOH. this now derived equation allows you to go from pH to pOH by using pH plus pOH equals 14, and this came from our kW calculation. So all of the equations that we use are actually summarized here. So we're going to kind of finish up with a calculation of this using this pH map. So we're asking, what is the hydroxide ion concentration in a solution that has a pH of 2.8? So we know that this is this an acidic, do you think, or a basic solution? Because the pH is low, below 7, this is definitely acidic. And we can still, though, calculate the hydroxide ion concentration in an acidic solution, because really any solution that's in water has both H plus and OH minus. So there's a number of ways of doing this. The easiest way to do this is using the pH map. Let's first find the pOH. We have an equation that says pH plus pOH is equal to 14. And so, if you want to solve for pOH, just rearrange it, put pH on this side, and pOH will be equal to 14 minus pH. In this case, 14 minus 2.8, which if you calculate should give you 11.2. This is pOH. In order to find the hydroxide ion concentration, then we can, if you take a look at your pH map, to go from pOH down to OH minus, we simply do 10 to the negative pOH using this equation. So your OH minus concentration is equal to 10 to the negative 11.2. Go ahead and plug that into the calculator, and you should get yourself a value of 6.31 times 10 to the negative 12th molar. And notice this is a very small concentration because we have ourselves an acidic solution, which makes sense. Now you could have also done this problem from the other way. You could have used kW, the definition of kW, and H plus times OH minus, and you could have undone pH. So you could have used this equation. You could have said that H plus is 10 to the negative pH. You could have used both these equations and still arrived at the right answer. There's two ways to go here. So if we go back, we began with a pH. Let me clear this real quick. We began with this value, and we were asked for this value. The way we went just now is we went this way. We went to the right and then down. You could have also went the other way. You could have went down and then to the right. So either way would have worked. In fact, you can try it on your own to verify the answer gives you the same value. Let's quickly finish up with a discussion of how we practically measure pH. A quick and dirty way is to use litmus paper. No doubt you've heard of the litmus test. And litmus paper will turn either blue or red. So you take a strip of litmus paper, red litmus paper, stick it in your solution. If it turns blue, then you have yourself a base. And if it turns red, you have yourself an acid. Now usually litmus paper is comes as red or blue. That way it's easier to see the difference. There is also neutral litmus paper that can turn either red or blue. But in general, this gives you a quick and dirty way of seeing. If you see red after you dip it in the solution, you get yourself an acid. And these are roughly the pH levels in which at which these color changes occur. A more convenient way is to use indicators, and we actually used a few of these, and we'll use more. And these will change colors in much more specific pH ranges. So, for example, bromothymol blue is a famous indicator that turns from yellow to blue at a pH range of 6 to 8. So if you have it turn in this pH range, these are very often used for titration experiments, which we will see. So you can get yourself a rough idea of where you are in the pH scale using indicators. And lastly, the best way to actually do this is using the pH meter. We have modern measurement devices, pH meters, so all you have to do is take your solution and stick a pH meter in it, and it will give you your pH. And the way it does this is by simply measuring the voltage of the solution, because all acids conduct electricity. So the more acidic it is, the more it conducts electricity, and that's able to use and measure your pH that way. So this should conclude for us lesson 2 of chapter 16.